Cephalopods include, creatures that most folks are familiar with, octopus and cuttlefish and squid. And their key characteristic feature that's of interest to us is, their skin and its spectacular capabilities in changing color and adapting to the coloration of their surroundings for the purpose of concealment. So it's a really, really interesting class of creature, and we've been intrigued and fascinated by their skin and the physiology, the function of that skin.
Cuttlefish and octopuses, they've been called the chameleons of the sea. How do they change color so quickly?
Well, it's really, kind of an interesting engineering construct, looking at it, through that lens. So if you look at the skin, it's a complex, multifunctional system. It consists of a top layer that provides the coloration, and it consists of an array of pigment sacs that contain different colored proteins. And those sacs can be moved by attached muscle fibers. So in that way, you can sort of adaptively, adjust color. But then underneath those pigment sacs are reflective layers, providing kind of a white background. But that's obviously not enough. You need as well a mechanism for sensing the color of the surroundings.
So tell me a little bit about this material you've made that incorporates the cuttlefish design for camouflage. How does it work?
Yeah, so it really is using the cuttlefish model as inspiration for overall architectures and engineering ideas that accomplishes the overall camouflage. So it includes a multi-layer layout like the cephalopod skin. It's three primary layers, each one of which has function that's analogous to what you see in biology. So as a top layer, it has a color changing type of capability. Instead of pigment sacs that are moved mechanically, we use a class of chemistry that changes reversibly upon slight heating. So if you increase the temperature of this by a few degrees, it undergoes chemical change that eliminates all absorption. So it goes from black to transparent, and it goes back and forth. Black to transparent is not good enough, to change appearance on its own. So we add in some bright white reflective base that serves as kind of an optical background. So upon heating, the visual appearance to an observer is a black to white transition. Just the color changing layer is not going to cut it. We need to couple that with an array of silicon-based elements for doing joule heating. So a slight amount of heating affects this color change in this chemistry and this black to white transition we talked about. But then you also need some kind of photodetector for sensing the color of the surroundings. There we use silicon photodetectors. The output of those photosensors, each one of which is located at each of the pixels in the array, couples to the actuator couples to the color-changing material to form something that has completely automated response to different lighting conditions, patterns of light, levels of illumination.
So just putting this all together, there are three layers, one of which senses the surrounding brightness, one of which controls the temperature of the material, and the third layer, the temperature controls that, and that changes the color of each pixel.
Yeah, that's exactly right. So again, that kind of multi-layer, multifunctional architecture is what you see in the cephalopod skin. So we've maintained those kinds of concepts, embodied them in different types of technologies, but functionally and architecturally it's very similar. So these are each very thin layers. They're stacked on top of one another in an aligned configuration. They're connected, so they're talking to one another and operating in a coordinated fashion. So the entire system is about the thickness of a sheet of paper. The appearance is kind of, like black ink on white paper. I mean, it's a very good type of contrast in that sense.
A material that changes color by itself sounds great. So what sort of applications have you been thinking about for this?
Well, a lot. I mean, I think the applications are kind of, some of them are sort of obvious. You might imagine that the military could be interested in systems of this type. You can imagine other things as well, however. We've been having conversations with a professor at the School of the Art Institute of Chicago, sort of an expert in fashion. So you can imagine, fabrics, for example, that are responsive to their surroundings in sort of a visual way that could be interesting, just from an aesthetic standpoint. We've also had conversations with folks in our School of Architecture. You can imagine if you have these color-changing sheets, you can wrap them on any kind of surface, right? So you can put them on the walls, you can put them on furniture, all kinds of stuff, turn out to be interesting to people who think about interior design.